Welcome to a journey unlike any other. We are tracing the most profound technological acceleration of the 21st century, the rise of the large language model, or LLM. But instead of diving straight into complex code and equations, we are going to explore this history through the lens of something familiar, something we understand instinctively: the automobile. This is The Road to AI, an automotive history of the LLM. Look closely at this beautiful vintage vehicle. It's not just a car, it's a schematic representing the core architecture of an AI model. In the front, the classic body symbolizes the input layer, the source material. As we move back, notice the data ingestion, those stacked coins representing the massive training datasets gathered from the 1930s to the present, the intricate web of gears and circuits running through the chassis. That's the neural network architecture, the mechanism that processes information. The flow translates raw data into algorithmic processing, leading to the rear wheel, the generative output. This output starts as predictive modeling and culminates in decision trees and the final result. We specifically feature the iconic 1930s Bugatti Type 57, a blend of revolutionary engineering and timeless design, mirroring how the foundational ideas of AI, though old, have evolved into something futuristic. Over the next few minutes, we will unpack how this seemingly simple mechanical structure evolved into the complex, self-driving AI agents of today, using the major breakthroughs in automotive engineering as our guideposts. Get ready to start the engine on this revolutionary history. Our history is mapped across 5 distinct eras, tracing the path from the rudimentary, horseless carriage of early computation to the sophisticated, self-driving agent we see today. Each era marks a fundamental leap in how machines understand and generate language, perfectly mirroring the transformative journey of the automobile. Our starting point is Era 1, the mechanical age, spanning everything before 2003. This was the era of symbolic AI and early rule-based systems. Think of it as laying the foundation, where we had structure, like a mechanical carriage, but lacked a dynamic power source. Next, we hit Era 2, the first engine, running from 2003 to 2015. This is the dawn of neural networks. Deep neural networks and techniques like backpropagation finally gave our models fuel and horsepower, allowing them to learn continuously. This was the Model T moment for AI. The attention mechanism, the first major modification, bridges this era into Era 3. The V8 moment in 2017, the Transformer Revolution. This shift introduced massive parallel processing, allowing models to grasp entire contexts instantly, defining the modern large language model. It was a complete redesign of the chassis. Following this power leap, Era 4, 2018-2020, ushered in the age of scale, marked by mass production and supercars, characterized by unsupervised learning and the rapid scaling of parameters. This is where models like BERT and GPT were first manufactured on a massive scale. Finally, we arrive at Era 5, the autonomous future, the current frontier starting in 2022. Here, models focus on continuous learning, multimodal AI, and agentic systems, evolving our LLMs into truly intelligent, self-guiding entities. This deck is your self-guided tour through these essential breakthroughs that define modern artificial intelligence. We begin our journey in Era 1, the horseless carriage, representing language before we had a true dynamic engine. Before the internal combustion engine revolutionized transport, we relied on mechanical contraptions. These were structured and ingenious, but they crucially lacked a dynamic, self-powered source. In the world of language modeling, this era, pre-2003, was all about counting, organizing, and cataloging parts, not generating power or dynamic prediction. Our first concept is the bag of words BOW model, which we liken to the vehicle's parts list. It represents text as an unordered collection of words, judged solely by frequency. You know exactly what's in the crate, the ingredients of the text, but you have no information on how those parts connect or their grammatical function. It completely lacks context and structure. Next, we refine this concept with TF-IDF, or term frequency inverse document frequency. This is about identifying the crucial parts. By weighting words based on their importance and rarity across a larger document set, TF-IDF improves on BOW, allowing us to highlight significance. A rare specialized tool is correctly deemed more important than a common nut or bolt. Finally, we introduced LSA and LDA, latent semantic analysis and latent Dirichlet allocation. These are clever gear systems. These methods used linear algebra and probabilistic modeling to organize the parts, capturing latent semantic relationships and topics beneath the surface. They could reveal structure, identifying that car and vehicle are related terms, but fundamentally, they still lacked self-powered prediction. They simply cataloged the structure of what was already there, unable to move themselves forward. Era 2 marks a monumental shift, the first engine, the dawn of neural networks. This is the point where our system starts consuming fuel, data to generate power, which means generating predictions. Early models were complex, but they were steadily refined with better components for improved performance and memory. The first true spark came in 2003 with neural language models, often likened to the Benz patent motorwagen. Bengio and his team pioneered the use of neural networks to learn continuous, dense word embeddings. This was the first concrete proof that a network could actually predict the next word in a sequence, providing the foundational spark needed to power our language machine. The engine became truly accessible and mass-producible starting around 2013-2014 with Word2Vec and GloV. We call these the Ford Model T. These methods introduced incredibly efficient ways for learning high-quality vector representations, enabling powerful embeddings, which capture the meaning of words mathematically to become widely accessible. This made deep learning feasible for broader tasks. But an engine needs a transmission and drivetrain to handle the road. This role was filled by RNNs, LSTMs, and GRUs, our drivetrain and gearbox. Architectures like recurrent neural networks RNNs were designed to process sequences, or the road ahead, one word at a time. The major engineering challenge was short-term memory loss over long sequences. This led to the development of LSTMs in 1997 and GRUs in 2014, which acted as advanced gearboxes, expertly addressing the vanishing gradient problem, allowing the engine to remember crucial information over much longer sequences of text, paving the way for more sophisticated communication. Now we arrive at a critical juncture, the turning point, giving the engine a new kind of vision. Even with the powerful LSTMs, our models still had a critical flaw: a fixed, forward-facing view. They processed text step by step, reading one word, making a prediction, reading the next. If a key context clue was 50 words back, the model had likely forgotten its full importance by the time it reached the end of the sentence. Consider the automotive analogy. Before modern sensor suites, a driver had a fixed, forward-facing view, restricted to what was immediately visible. The breakthrough of the attention mechanism, introduced by Bodenau et al. In 2014, is like giving the driver the ability to instantly glance in any mirror or turn their head to focus on the most relevant car or sign, no matter how far away it is on the road. This power of selective focus was the crucial precursor to modern LLMs. The LLM breakthrough resulting from the attention mechanism was revolutionary. It freed models from the rigid, step-by-step processing inherent to RNNs. It allowed the model to look back across the entire input sequence, not just the last few words, and dynamically assign importance scores to each word based on its relevance to the current prediction. This dynamic weighting mechanism created a vastly richer and more holistic understanding of long-range context, fundamentally changing how context was processed and finally setting the stage for true intelligence in language modeling. The attention mechanism was the catalyst for the single most defining architectural shift in AI history, ushering in Era 3. The V8 moment, the Transformer revolution. The Transformer is not merely a better engine. It is a complete redesign of the car's core mechanics. It decisively replaces the slow, sequential, one piston at a time drivetrain of RNNs with a massively powerful, parallel processing V8 engine built on a revolutionary new chassis. This entire movement is encapsulated in the famous 2017 paper, "Attention is All You Need." The central achievement of the Transformer was the elimination of recurrence. The old RNN LSTM schematic, the sequential gearbox, was discarded entirely, as indicated by the faded, crossed-out image. By relying purely on attention and dispensing with the need to process tokens sequentially, the V8 engine could fire all its pistons simultaneously. This breakthrough in parallel processing meant models could be trained exponentially faster on much larger datasets, utilizing the full, parallel power of modern GPUs. At the heart of the transformer engine is self-attention. This is the engine's core operating principle. Every word in the input sequence could now directly look at and instantly relate to every other word in that same sequence. Instead of building context word by word over time, the model received a rich, holistic understanding of the full context right from the outset. This is the mechanism that finally unlocked the massive scale and power we now associate with large language models. With the V8 transformer design perfected, Era 4 arrived, hitting the assembly line, pre-training, and the first modern LLMs. The technology was finally reliable, powerful, and ready for mass production. Pre-training became the automated, massive-scale factory, and the models were the first high-quality vehicles to roll off the line, ranging from reliable sedans to powerful sports cars. This era was defined by the new paradigm of pre-training and fine-tuning. The strategy became utterly dominant because of its efficiency. You build 99% of the car on a general assembly line. That's the massive pre-training step, where the model learns generalized language patterns from enormous amounts of internet text. Once that general, powerful car is built, you customize it for a specific job. That's fine-tuning, specialized painting, or adding features for a specific customer. This two-step process unlocked unprecedented scale and capability. Two foundational models rolled off this assembly line in 2018. First, BERT, Devlin et al., 2018, the reliable workhorse. BERT utilizes the transformer encoder architecture, meaning it is bidirectional. It looks both left and right in a sentence simultaneously. Its primary function is understanding and analysis, becoming the industry standard for deep contextual understanding. Secondly, we had GPT, Radford et al., 2018, the first-generation sports car. GPT uses the transformer decoder architecture, which is causal. It only looks backward, simulating generation. Its primary function is generation and prediction. GPT immediately set the stage for a new class of powerful generative models, hinting at the high-performance vehicles that were soon to come. Having perfected the assembly line, the competition immediately escalated into the supercar era, the pursuit of unprecedented power. This was the horsepower race of the 1960s, but instead of chasing cubic inches in the engine block, we were pursuing parameters in the models. Parameters are the engine components, the values the model learns. The hypothesis was elegantly simple. Bigger engines unlock more capabilities, more sophisticated behaviors, and better reasoning. The results were absolutely breathtaking. In 2019, we saw the launch of GPT-2, the exotic supercar. With a parameter count of 1.5 billion, GPT-2 scaled up the causal GPT architecture and showed what was called zero-shot performance. This was the shocking ability to perform complex tasks, like summarization or translation, that it was never explicitly trained for asterisk. It was the first undeniable hint that scale alone was unlocking generalization, not just memorization. Then, just 1 year later, in 2020, came the hypercar, GPT-3. Jumping to a monumental 175 billion parameters, GPT-3's performance was a staggering leap. It could generate remarkably coherent text, write functional code, and most importantly, learn from just a handful of examples, a capability termed few-shot learning. This achievement began blurring the line between simple pattern matching and true, abstract reasoning. As you can see on this log-scale graph, the parameter count, directly analogous to the size and complexity of the engine, did not increase linearly. It exploded exponentially. This era of massive scaling proved that compute power, driven by the transformer, was the key to unlocking true artificial general intelligence. As we enter Era 5, the smart car adding senses, safety, and efficiency, the focus shifts dramatically. The race is no longer solely about raw horsepower. It's about making the car smarter, safer, and infinitely more efficient. It's about what the car can truly do with its power in the real world. A critical development for safety and alignment came in the form of instruction tuning and RLHF, reinforcement learning from human feedback, which acts as the advanced driver assist system. LLMs are powerful, but early versions often produced outputs that were toxic, unhelpful, or biased. RLHF acts like a crucial safety system, using human preferences and detailed feedback to align model outputs with desired values and instructions, ensuring the models follow human instructions reliably and safely. We also see the expansion of sensory input through GPT-4 and multimodality, 2023, the adding a full sensor suite. Suddenly, the car can not only read text but also see images and process code. This represents a significant leap in robustness and capability, allowing the LLM to interact with the world through vision, code, and language simultaneously. Finally, to ensure this complex system runs efficiently, we adopted the mixture of experts MOE architecture, or the hybrid engine. MOE is a more efficient design that uses smaller, specialized subnetworks, or experts for different tasks, like language, vision, or logic. Only the relevant experts are activated for a given task, enabling the creation of larger, more powerful models with better performance, but significantly lower computational cost compared to monolithic models of the same size. We have reached the destination, full self-driving and the rise of agentic AI. This is the ultimate goal of the road trip. The ideal LLM, the fully autonomous vehicle, can receive a complex destination or achieve this objective and navigate the entire journey on its own. It doesn't wait for turn-by-turn prompts. It makes its own high-level decisions, uses its tools, like GPS for planning, turn signals for execution, and handles complex, multi-step trips without constant human intervention. The current cutting-edge technology, the true frontier of LLMs, is defined by agentic models, exemplified by systems like GPT-4v and Gemini. These systems are fundamentally different from models that merely respond to prompts. Agents are designed for reasoning, planning, and tool use. They can analyze a high-level request, for instance, plan a trip to Paris, book flights, and check weather, break it down into discrete, manageable steps, and then execute those steps sequentially. This execution involves using external tools, whether that means writing and running code, browsing the live web for information, or accessing external databases. Critically, these agents are designed to learn from the results of their own actions, closing the feedback loop and making them increasingly capable of handling true real-world complexity and achieving goals autonomously. This ability to reason and act defines the next generation of AI. As we look back on this incredible journey, we must acknowledge the visionary engineers, the architects of the revolution. A technology's evolution is rarely anonymous. It's a human story driven by key individuals and teams who design the fundamental engines, chassis, and assembly lines of the modern large language model. Starting with the first Spark, Bengio et al., 2003, they were the pioneers of the neural engine concept, proving that continuous word embeddings were possible and providing the foundational spark. Next, the essential Gearbox. Hochreiter and Schmidhuber, 1997, the inventors of the LSTM, the long-term memory gearbox that made sequence processing reliable and solved the memory problem inherent in early networks. The definitive leap forward came with Vaswani et al. 2017, the designers of the revolutionary V8 transformer engine, whose paper "Attention is all you need," changed everything by enabling parallel processing. Following the engine redesign, we needed mass production vehicles. Devlin et al. 2018 created BERT, the ultra-reliable transformer encoder workhorse that became the industry standard for language understanding. Finally, the pursuit of power and generation was led by Radford, Brown et al. 2018-20, the engineers who built the game-changing GPT series supercars, proving the immense potential of massive scale in generative models. These individuals provided the foundational breakthroughs that paved the road we travel today. We conclude by reflecting on the fact that the journey continues. The evolution we have witnessed, from mechanical calculation and word counting to autonomous reasoning, represents one of the most profound technological accelerations in history. Let's summarize our journey through 3 key points. First, the journey traveled. We have dramatically progressed from the simple, horseless carriage of probabilistic word counting to the full, self-driving potential of agentic AI. The early days focused purely on organizing discrete parts. The current era focuses on reasoning and autonomous goal achievement, shifting the paradigm completely. Second, the core drivers. This revolution was fueled by a fundamental, two-part shift. It was defined by the architectural breakthrough of the transformer, which enabled massively parallel processing, and it was supercharged by an unprecedented, unwavering commitment to scaling both the data used for training and the compute required to process it. Third, the road ahead. The future points towards several critical innovations. We anticipate even greater levels of autonomy in our agents, more efficient engines thanks to new architectures like Mixture of Experts, MOE, and crucially, deeper integration with the real world through enhanced sensors via multimodality. The final destination of artificial intelligence is unknown, but the exhilarating, breakneck pace of innovation is undeniable. Thank you for taking this ride with us on the road to AI.